Hello, my name's Alan Foom, and this is part 2 of my talk on Geodesy for Geologists. This part I'll be talking about latitude, longitude, and ellipsoids. So what is a coordinate system? So this is a diagram explaining how that all works. You will have an x or an easting, which is distance east from a datum point. A y or a northing, which is the distance north from a data point, as seen on this diagram. Z is the elevation or distance above or below a datum, for example sea level. So these are what was used in coordinate systems such as Universal Transfer Mercator, UTM, or the British Ordnance Survey. So for a coordinate system we require an ellipsoid, a projection, a datum, and a zone. So this is a diagram which shows you x and y and z, which describes how a coordinate system works. So latitude and longitude, if you remember from school, latitude is a geographic coordinate north-south direction, which is defined as an angle relative to the equator in degrees. So for example, the equator is 0, the North Pole is plus 90, and everything in between. Longitude is defined as the coordinates in the east-west direction. It's defined relative to a prime meridian. The world's prime meridian is in Greenwich, but if you look at some data from before the 19th century, before this was agreed, other people use other prime meridians. So you will have a certain degrees west and a certain degrees east. So sounds fine, and a lot of people think that latitude and longitude are unique. They are not. Repeat, not. This is an example from the UK Ordnance Survey, booklet on surveying, and it shows the position with the same lat longs based on 3 different coordinate systems. So this is ED50 or European Datum 50. This is OSGB 36, which is what people use for the national grid in the UK, and this is WGS 84. Now they're all within 200 meters of each other, which may not sound too much to a lot of people, but when you're locating an oil well, or you're locating a mine, or locating other buildings, or locating, for sake of argument, disposed ordnance, you really would need to know that. So, key point here is latitude and longitude are not unique. Even when you look at a prime meridian, that's not necessarily in quite the right place. Here's a photograph of a bloke with a GPS. He's standing in Greenwich, so that line here is the prime meridian, and you can see that that is not 0, 0, 0. And the reason is that the current prime meridian is not quite the right place. Now, it was calculated originally in 1851 using an ellipsoid, I think it was the area ellipsoid, but the ellipsoids that are used now mainly are a little bit different. So the prime meridian actually shifts 101 meters to the east, and modern GPS I think uses WGS 84, which is different, which is why you have this particular situation. So what is an ellipsoid? Well, Earth's not a perfect sphere. It's squashed a little bit at the poles, so it's called an oblate spheroid. But nobody's quite agreed exactly how much squashing there is. So different spheroids exist because different mathematicians have done different estimates of how round the Earth actually is. So what you would have are 2 factors here. One factor called the semi-minor axis, which is north-south, and a semi-major axis, which is east-west, because the Earth is flatter at the poles than it is at the equator, which is why if you want to be furthest away from the center of the Earth, you'd go to a large mountain on the equator, something like Kilimanjaro, or I think there's a mountain in Ecuador which may even be taller. The WGS 84 ellipsoid, for example, has these particular parameters, so semi-minor axis, semi-major axis, and degree of flattening. And different ellipsoids exist in different countries. So for example, here's a list of very common ellipsoids which are used throughout the world. Everest 1830, which was done by George Everest, the man who postulated Mount Everest or Jomolungma in India. So that's still used very much within India. The Airy spheroid in 1830, used in Britain, which is what the Greenwich meridian was originally defined in. The Clark spheroid used in North America, and a lot of American companies use it around the world. It's a very good approximation for North America, but less so elsewhere. 1924, people had a go at producing a spheroid, a common spheroid, the international spheroid, also known as the Hayford 1909. That's used quite a lot within Europe. So ED50 uses that, for example. Then there's the Krasovsky spheroid in Russia and former Soviet Union, which was developed by Krasovsky in 1940. Then there were several other attempts, culminating in WGS84, which is used by GPS, which is now trying to become the world standard. However, there's a problem because countries tend to be very proud of the spheroids, particularly if they're done by their own national mathematician, and country systems are enshrined in law to some extent to use a particular way of doing things. So different spheroids are used in different places, and you must use the appropriate spheroid for your area, or at least know what spheroid is being used. So now we'll move on to part 3, which is looking at datums. So a datum is a fixed point, and it's used to reference a coordinate system. The horizontal datum is the point of reference, so it's generally a marker in the ground, such as Meads Ranch in Kansas, and we'll come to that in a minute. Vertical datum is a plane to which heights are referenced. So various geodetical datums exist. So for instance, ED50 in Europe is centered on the Potsdam Observatory near Berlin. And NAD 27 and NAD 83 are used in North America. They're centered on a place called Meads Ranch in Kansas, but they use slightly different ellipsoids. And note also that NAD uses feet rather than metric. Most systems use metric, but the Americans use feet. Or to be even more nightmarish, survey feet, but we'll come to what the difference is in a minute of those in a minute. So these are North American datums. They're both centered on Meads Ranch in Kansas, so there's a picture of somebody important standing at the Meads Ranch marker, there's a picture of the marker, and this blue star is where Meads Ranch is located. And the datum shifts used between NAD 27 and NAD 83, which can vary. You're talking to some extent up to 80 meter shifts when you're moving towards California. So making sure that you have the right datum as well as the right spheroid is obviously quite vital. Then looking at vertical datums. So this is a map of Europe with different vertical datums. And most state countries use sea level. There's a minor problem with that because no one can quite agree on where sea level exactly is, and different countries, as you can see from the map, have slightly different definitions of it. Generally, it's taken from a tidal marker somewhere along the coastline, and everything is then referenced from that. WGS84 uses an ellipsoid as the datum, so from reference ellipsoids, everything's measured up and down relative to that. Some rare coordinate systems use the geoid, and I'll explain what the geoid is in a minute as well, where they use that as a datum. So you need to know what you're using vertically as a datum. Also, if you are in places where you're significantly above sea level, for example Algeria or Bolivia, the seismic reference datum might be 100 meters above sea level, 200 meters above sea level, etc. And if you're working in the Caspian, so if you work in Kazakhstan or Turkmenistan or Azerbaijan, they would use Caspian sea level, which is 27 meters below Baltic sea level, as the datum there. So again, that's something to bear in mind. So this is just another example. You have mean sea level or lowest astronomical tide, which are close enough, but there is quite a difference between that. Heights above the geoids, heights above ellipsoids, etc. So needing to understand and know what your relative heights are. And then we have the geoids. So a geode is a surface of equal gravity potential. So that's where gravity tends to kind of line up. And can be used as a vertical datum. And if all the world's oceans were under gravity and atmosphere were at equilibrium, that's kind of where it ends up. So the variations due to difference in rock density, local geology, etc. And the surface is not regular, unlike an ellipsoid, which is effectively regular. I was going to say flat. It isn't flat. Obviously, it's curved. So geoid can vary up to 106 meters below or 85 meters above to the reference ellipsoid. So geoids are to bear in mind. Geoids are something that you would need to bear in mind. Although most people would tend to use an ellipsoid or a datum marker for your vertical datums. So here's a picture of geoid height. So for instance, particularly low in the Indian Ocean, particularly high in the North Atlantic Ocean. So it's basically the Earth is quite rugose. So thank you very much, and in part 4 and 5, I'll talk about coordinate systems and map projections.